Good afternoon, everyone, and welcome to the Arizona State University College of Health Solutions Biomedical Informatics Seminar Series for 2021 Fall. I'm your host, Dr. Anita Mirko, and coming to you with our BMI 570 class today from the very beautiful ASU Health Futures Center in Phoenix, Arizona. As you probably can tell, the seminar is being recorded. So very important for you to place your mic on mute. If you have a question, please use the chat function. And if you are in the room here, please make sure that your devices are on mute or turned off. We are very proud today to welcome back to ASU, although virtually, Dr. Zhongwei Zhao. He's a 2021 graduate of the ASU Biomedical Informatics PhD program. Dr. Zhao studied under Professor Jiming Liang, and he focused on new methodologies for annotation in computer-aided diagnosis and medical imaging. As you may have noticed if you read the Outlook invitation, he has a very impressive graduate career. He published 10 peer-reviewed articles. Several of these articles have received prestigious awards, and 2 of the articles hold the distinction of being the most popular downloads in these journals. Dr. Zhao has 12 US patents pending and plays an active role in the leading societies of computer vision and medical imaging. Today, he is Zooming to us from Johns Hopkins University, where he is now a postdoctoral researcher with the Bloomberg Distinguished Professor Alan Yu Lee. Today, he's going to talk to us about his research in annotation-efficient deep learning for computer-aided diagnosis. So let's give him a warm welcome back to ASU.
Thank you. Can you hear me?
Very well, yes.
Okay, thanks a lot. Hello everyone, good afternoon. I'm Zhongwei, and I just received my PhD degree this year in May, and from Biomedical Informatics Department. And my advisor is Dr. Jiming Liang, who is a very good advisor. And today I will present the work I have done during the 5-year PhD program at ASU. And the title is Towards Annotation-Efficient Deep Learning for Computer-Aided Diagnosis. Medical images account for about 90% of all healthcare data. And the number of medical images are increasing rapidly over years. We believe computer-aided diagnosis can be a great tool for doctors to release their increasing workload. And it can also make a great impact for early disease diagnosis and detection. In the last few years, deep learning methods have been dominant for building a computer-aided diagnosis system. We can use a deep learning model to identify, localize, or measure the disease in an image. This method shows promising or even sometimes amazing results in several medical tasks. I gave you 3 successful examples here, using deep learning method to deal with lung cancer, diabetic disease, and skin cancer. These studies demonstrate deep learning can achieve a human-level diagnostic precision. However, developing such deep learning models needs a huge amount of annotation cost. These annotations are largely done by human experts. For example, to identify lung nodule from the CT images, human experts have to annotate where is the nodule, how big it is, whether it's benign or malignant. To achieve human-level precision, this study utilized more than 42,000 radiologist-labeled CT images for just one disease, lung cancer diagnosis. And a similar story applies for other disease detection. Annotating medical images is not part of a doctor's routine workflow. just used for train computer. Also, annotating medical images is tedious, time-consuming, expensive, and require medical expertise. Not everybody can do that. So annotation is very important for developing high-performing deep learning method. And it is also one of the biggest barrier when people want to apply deep learning to other diseases. So this work, I try to answer the question, how to develop annotation-efficient deep learning without such big annotated data. Computer-aided diagnosis of a real disease and quickly response to global pandemics are severely underexplored because of the difficulty to connect such big labeled data set, especially when a flow of patients are waiting for results during an outbreak, and the doctors do not have time to annotate every cases for algorithm development. And not many doctors actually have an expertise for the novel and the real disease at the very beginning during the pandemic. So this diagram shows the simplified workflow, how people apply deep learning into the healthcare in practice. First, we obtain annotation from human experts, and then we train the deep model using these annotations. And third, after all the developing validation, we can deploy the deep model into the clinical practice and perhaps to the hospitals that lack of expertise. To optimize this workflow and to quickly build an efficient system, my research goal is to develop method to minimize the manual annotation effort. To do so, I have outlined 3 specific aims. The first aim is to smartly acquire necessary annotation from human experts. Second, with certain amount of annotation, I utilize this annotation efficiently by designing advanced deep neural network architecture. And finally, extract the generic knowledge directly from the unlabeled, unannotated images. In general, the performance of deep learning will increase as the annotated data increase. This is the reason why we always love to collect more data and more annotation. But there comes a plateau here. When adding more data, the performance improvement might not be significant. But this usually does not apply in medical imaging field, because it's not easy to get millions of annotated medical images by a human expert. Now we try to make this curve much better. Aim 1 suggests that by selecting the most representative and informative samples, deep learning is able to learn faster than random selection. Aim 2 suggests that by designing advanced architecture, we can improve the model capacity and lead to a higher performance. And Aim 3 suggests that by using the generic image knowledge, medical knowledge, the model can behave much more robust, even trained with a small amount of annotated data. Overall, we hypothesize that with a small part of a dataset annotated, we can deliver deep models that can match or even outperform those models that require annotating the entire dataset. So this is called annotation-efficient deep learning, as suggested in the title. And this hypothesis can be interpreted into 2 ways. First, by maintaining the high performance, our method requires less amount of annotation. As shown here, the gap represents the number of annotation costs that can be reduced by annotation-efficient deep learning. And second, by using the same amount of annotated data, our method can achieve much higher performance as shown in the vertical line gap. So putting these two perspectives together, I will demonstrate the annotation efficiency of our method in the rest of the talk. I'm mainly focused on the methodology and algorithm development. That means the devised methods are supposed to be generalizable to different applications. So to validate the hypothesis, we have used 12 different use cases in this work, including disease detection, segmentation, and classification, and covering the medical modality such as CT scan, X-ray, and colonoscopy, microscopes, MRI, ultrasound, and so on. So now let's dive into each of the specific aim. If you have any question, please let me know in the chat box or in person. So the first aim is to select the necessary samples for annotation. Medical images are generated every day in hospital. With limited budget and time, it is infeasible to annotate each and every clinical image that we have. So we try to find an important subset of the image for human expert to annotate. The common approach is called human-in-the-loop active learning procedure. It incorporates both the human expert and the deep model together to precisely detect disease. Give a pre-trained model, we first test it on the huge amount of unlabeled images and get the prediction. Based on the prediction, we select the most important images and send them to human expert for annotation. Then the annotated image will merge into the labeled set and use this data to fine-tune the previous model and get the prediction from the updated model again. Then we select most important image again for annotation. As you can see, this become a loop. So it's come human in the loop. The key challenge in this loop is how to select the most important image. Here I give an example to classify a sample from flu and healthy person using two symptoms. First, the body temperature, and second is a muscle ache. All of the dots here with color means annotated samples, which means we know their label. So here the green is healthy and the red is flu patient. So A and B here are two unlabeled samples. So now the budget allow us to only annotate one patient now. So which sample would you prefer to annotate first? A or B? If we look at A, we do not expect the major change of decision boundary like here when annotating sample A, because this sample is somehow confident that the current model will group it as the diseased patient. But for the sample B, whether it's diseased or it's healthy, it will dramatically change the decision boundary, as shown here. Therefore, at the moment, sample B seems to be more important to be annotated than sample A. And we can measure the importance of these two samples based on their uncertainty. This approach is generally called uncertainty-based selection, which always select the sample with high uncertainty. So in this case, B, the current model is not certain whether it's healthy or flu. Another selection criteria is called diversity-based selection. The idea is to select the most diverse or representative samples to be annotated. Here we have a sample B, C, D here, and they all very uncertain because they're in the decision boundary. So now the budget allow us to only annotate 2 out of these 3. So which 2 would you prefer? BD, BC, or CD? So if we select the CD, you can see they are very similar in the feature space. So it's somehow you wasted this $2 to annotate this very similar samples. But if you annotate BD or BC, because they are far away, so it looks like you are using money to annotate more, to have a more value. So we can quantitatively make the decision by computing the diversity of each samples. As a result, BC shows the highest diversity, and BD is okay, but CD are too small, too similar. So we should choose BC in this regard. Diversity-based approach aim to select new samples to be annotated in which they are very different from each other and they are different from existing labeled samples. To realize this, we create a diversity matrix where each row and each column represent the samples in the dataset, and the cell in the matrix is the similarity between the 2 samples. For example, here is the similarity between the sample A and C. The goal is to find the submatrix that have the largest diversity or smallest similarity compared with the entire matrix. It looks very easy, very straightforward, but in the real world application, not the case. Because this matrix is super big, the number of row and the number of column are equal to the entire number of images in the data set. It can go to million or even more. So solving this optimal submatrix is an NP hard problem, and it's computationally intractable. So our contribution is to compute diversity more efficiently with the help of data augmentation. As shown here in the figure, data augmentation refers to augment multiple patches from the original image. This approach is widely used in medical imaging and also computer vision because we usually do not have enough training data. Data augmentation is a great way to automatically generate many data for us. These patches generated from the same image should share the same label. For example, here, all the augmented patch should correspond to cat, and they are expected to have a similar predictions by the current model. With this assumption, we can just measure the consistency of the prediction for the same image. If the predictions are consistent, we find that the model is pretty sure about the image, and so no need to be annotated at the moment. If the predictions are inconsistent, like sometimes the model say, oh, this is a cat, sometimes it's a mouse, sometimes a dog, sometimes snake, then that means the model is very, very uncertain about this image. Then we think this sample should be annotated first. So instead of build the huge diversity matrix, we can simply compute the consistency of the small matrix associated with each sample. Computing these small metrics is manageable and effective because the number of row and the number of column represent the number of augmentation for each sample, which usually only 10 or 20. And we are able to discover the most representative and informative samples through this approach. So we hypothesize that wisely selecting important sample can dramatically reduce annotation cost. And this gap again shows the amount of annotation that we can reduce by active selecting the sample to be annotated. And our study in the real medical data have confirmed the hypothesis. Here, the solid line is the upper bound performance that we can achieve. The y-axis is the accuracy, and the x-axis is the percentage of labeled data that we need. And we here the red dot is our proposed method, and the gray one is the randomly selection. So they do not care which one is important, which one not. So you can see we concluded that using our active learning selection method, the annotation cost can be reduced by more than 80% compared with random selection. I should note that the x-axis is a log scale. So this part looks very small, but it actually presents a large gap of annotation reduction, because here is around only 16% of data, and here can up to 66% of data. The limitation is that the current active learning procedure can only suggest the important lesion every time. If a patient contains multiple lesions, the active learning procedure might suggest to annotate the same patient multiple times, and each time on a different lesion. This means the human expert has to repeat going through the same patient multiple times, again and again. So it's somehow waste of effort. So we further propose to suggest the most important sample in a patient level. By transition from the lesion level to patient level, doctors do not have to repeatedly going through the same patient multiple times to detect all the disease that the patient might have, but they can only go through once and annotate all the disease simultaneously. This work suggests that not all data are created equal. Our job is to find the most essential data that can increase the deep learning model performance with as lowest annotation cost as possible. And AIM-1 has led to 3 publications. We first presented this work in 2017, which was also one of the earliest work I have done at ASU. And we apply this technique to many other medical applications and also validate the usefulness in natural imaging tasks. This work have a potential clinical impact because the continued learning capability of deep model encourage data, label, and model reuse, therefore significantly improve the training efficiency. And the efficient human-in-the-loop procedure assisted radiologists in quickly dismiss patients with negative results, therefore dramatically reduce the burden of annotation. Finally, an instant online feedback procedure make it possible for CAD system to be self-training, self-learning, self-improving via continue fine-tuning. After collecting certain amount of annotation, My second aim is to develop advanced deep neural network architecture. This is important because a better model architecture can lead to a higher performance in disease classification, segmentation, and detection. Here I use the image segmentation as the example. Image segmentation is a task to partition an image into multiple segments to ease the analysis. And it helps quantitatively measure the size of lesion and can make the surgery more precise. And people also use a deep learning method to automatically segment the organ and the disease from the images. The most popular architecture for image segmentation is called a UNet because it looks like a big U. The input is the original medical image, and the output is the segmentation mask of the target object that you are interested in. For example, here we are interested in liver and the liver tumor. So here the red area is the segment of the liver organ, and the green area is the liver tumor. UNet have two major parts. One is encoder, another one is a decoder on the right. So the encoder will map the image into the deep latent feature space, and the decoder will map the feature into the segmentation mask. So let's take a closer look at this architecture. As you can see, UNet, it can extract different level of image feature. So we hypothesize that by aggregating multiple scale of image feature can lead to a better model. So here scale, I mean this array. So the original UNet only used the level 4 feature, but we try to also take level 3 feature, level 2, level 1 into consideration. Why is so? We compare the performance of UNet with different level. So this is original UNet with 4 level, 1, 2, 3, 4. And we compare the UNet with level 1, level 2, level 3, level 4, because they're using different level of image representation. We tested on 3 different medical applications: neural structure segmentation, cell segmentation, and brain tumor segmentation. The result shows it is inconclusive which level of image feature contributes the most for different applications. For neural structure segmentation, it seems to be level 4 can give the best performance. But for cell and brain tumor segmentation, level 3 actually gives the best performance. So the best depth, best level is actually unknown in the literature. This is the motivation behind our new architecture called UNet++, which aggregates multiple scales features from different level of network, therefore resulting in a significantly better segmentation performance compared with each individual UNet. We call it UNet++ because it's offered 2 notable innovation. The first innovation is the redesigned skip connection to encourage different level of image feature aggregation. And the second innovation is the introduction of deep supervision. In contrast to the original UNet architecture, UNet++ provide additional supervision for each level of image features. So we found deep supervision can stabilize the model training, and more importantly, it also enable model pruning during the deploy time. People always complain that deep learning have so many parameters and it takes a large memory and a computational power. This is too much for ordinary desktop or laptop PC in the clinical practice. Our UNet++ can be pruned during the deploy time based on the clinical need. That means these branches can be cut after model training, and the leftover subnetwork can still perform precisely thanks to the deep supervision. We evaluate our UNet++ on 5 different segmentation tasks, including neural structure, cell, nuclear, brain tumor, and liver segmentation. The red bar is our UNet++, and the gray and the yellow one is the original UNet, and the UNet Plus here is the intermediate architecture. So this UNet Plus is a simplified architecture to the UNet++, but still can produce great segmentation result. We compare these 3 architecture using more sophisticated feature extractor, such as VGG19, ResNet 152, and DenseNet 201. Statistical analysis shows our UNet++ significantly outperformed the original UNet on every task. Besides so many technical detail and the quantitative result, let's look at how good the UNet++ segment liver organ and the liver tumor from CT images, for example. This is a patient with liver tumor. The left figure shows the original CT images, which is input to our model. And the middle one shows the ground truth given by human expert, annotating the liver and the tumor region from the CT images. And the right figure shows the prediction of our UNet++. The first point I would like to make is the prediction of UNet++ is very similar to the human annotation. And the second point I would like to emphasize throughout my talk is annotating work is extremely time-consuming and costly. You can easily find from this example, giving ground truth. Giving ground truth is a time-consuming job, so the doctor needed to go through every image slice and give the boundary of all the organ and disease. So we should really appreciate they give us this effort and give us these resources to train our model. And this effort will eventually make good contribution because the UNet++ trained with the expert annotation can do a great job in segmenting many more unseen patient CT images, which in turn can reduce the radiologist workload in the future. I'd like to show you another example. So this patient have a healthy, this guy have a healthy liver in general, but with a very tiny tumor in the middle. Our UNet++ is able to, let me see, I think the tumor is here. If you see here, the bright dot is the very small tumor. And our UNet++ is able to identify this small lesion. This is very encouraging result because it shows that our UNet++ not only sensitive to detecting different size of liver tumor, but also shows very high specificity, which means if it's a healthy liver, UNet++ will not generate too many false positives. As here, all the healthy liver and the prediction is healthy liver. All right. So try to conclude this work. Deep neural network learns the visual representation through multiple levels of image representation. And this study advises us that we must fully integrate each and every level of representation for more precise and comprehensive result. We first present UNet++ in 2018, and then extend this work into a journal publication in 2019. This article was ranked as one of the most cited, most popular ones in IEEE PMI journal. And this work have a potential clinical impact because image segmentation task itself can help compute clinically more accurate and desirable image biomarkers and precision measurement. Also, model pruning has the potential to exert important impact on deploy CAD system to mobile devices and the ordinary desktop, laptop, PC on clinical practice. In addition, we have a make UNet++ open science. We release the code and the model to the public and let others to play around. I'd like to share some of the results obtained from other independent research groups who used UNet++. As you can see, UNet++ achieve notably higher performance than the original UNet on more variety of tasks, such as COVID-19 segmentation, fiber, tracing, spleen segmentation, and so on. And these tasks are using different imaging modality, such as the CT, MRI, and microscope, fundus image, and so on. This also shows the robustness and the generalizability of UNet++ on different medical specialties, not only just the 5 applications that I showed you before in our paper. I will always very happy to see other team adopt our UNet++ for different purpose and applications, and perhaps producing even stronger algorithm architecture on top of it. So far, we have only discussed how to use annotated image, but it is also important to recognize the power of unannotated images. Therefore, my third aim is to extract the generic knowledge directly from the unlabeled images, so that the deep model can transfer this generic knowledge to many other imaging tasks. Now, how to extract this general knowledge? We observe that medical images are embedded with consistent and recurrent anatomical structure. So we hypothesize that using this information, we can empower deep models with generic and transferable image representation. Here shows the diagram of our proposed framework. We designed it as a simple image restoration task. Give a medical image, we first deform it in some way, and then feed into a deep model, let the model learn to restore the original image. To deform the image, we propose 4 different image transformation approaches, including nonlinear transformation, local pixel shuffling, outer cutout, and inner cutout. Each of them allows the model to learn from different perspectives. For example, it can learn organ appearance, organ texture, local boundary, and organ spatial layout and geometry, and many, many more. We found that learning from multiple perspectives can help build generic and transferable models. Actually, we are the first to build a generic pre-trained 3D model for medical image analysis. We called it Models Genesis. It learns representation directly from the unlabeled images without any human manual annotation, and it leads to powerful target models for many medical imaging tasks through transfer learning. This is the existing pre-trained model before us. So as you can see, they all need a huge amount of annotated subjects or even video. The first one is released by Google DeepMind. It was pre-trained on natural image with more than 240,000 annotated video. And the third one is from medical image domain. Second one called NiftyNet. It was pre-trained on 90 annotated subjects. And the most recent one is from Tencent. It's called MedicalNet. It is pre-trained on more than 1,000 images. So different from all this previous work, our models genesis are pre-trained on 0 annotated data. So models genesis shows higher precision and more robust performance than existing methods that I reviewed previously on 5 different medical applications, including lung nodule false positive reduction in CT scan, lung nodule segmentation, pulmonary embolism false positive reduction, liver segmentation, and brain tumor segmentation here in MRI images. We pre-trained the model's genesis on more than 800 chest CT images without a human label, and then transfer the image representation to different target applications. We compare model's genesis with other works, including random initialization, fully supervised pre-training, and existing self-supervised pre-training. The bolded number means the best one that we can achieve. And the cell highlighted in blue means these two performance have no significant statistically different. Has no different, yeah. In all 5 applications, models genesis shows the most robust result and sometimes hold the best result. Models genesis is an annotation-efficient method because for every task, as you can see, model genesis can achieve the same accuracy by using less amount of annotated data. So for example, here, pulmonary embolism false positive reduction, ECC. The red curve is using our model's genesis, and the gray curve is not used, random initialization. And you can see to achieve the similar performance as random initialization, we only need 55 fewer labels to get this performance. And the same story happened in other 4 applications. So in total, we found that it can reduce by at least 30% annotation cost. Our model's genesis shows generalizability within the same image modality. That means if the model is pre-trained on chest CT images, it is more beneficial on the target task that is happened in the chest area and in the CT modality. Therefore, in the future, we intend to collect the medical image from different modality and pre-train modality-oriented generic models for improved performance in that specific modality. Moreover, we want to collect medical images from different body regions and pre-train organ-oriented generic models for improved accuracy in that particular body part, such as genesis lung, genesis liver, and genesis brain, etc. So we hope this effort will lead to the holy grail of models genesis to learn effective image feature across disease, organs, and modality. This work was the first presented in 2019 and received a Young Scientist Award in MICI conference. And this work was also published in Medical Image Analysis Journal and received the Best Paper Award. And right, this work have a great potential clinical impact because instead of building a model from scratch, which demand numerous data and labor cost, a smaller data set can be used to efficiently fine-tune the existing model. And the generic pre-trained models can serve as a primary source of transfer learning for many medical imaging applications, leading to accelerated training and improved performance. We make the development of model genesis open science as well, and invite the researchers around the world to contribute to this effort. Again, these results are produced by other research group, not from us, and who they use our released code and models. I think by fine-tuning our models genesis, MG here, it can achieve significant performance gain in many other applications, both in the task of disease segmentation and the classification. The improved performance are obtained from different image modality, such as CT, histology, image, MRI, and others. I wish more teams will find the model genesis useful, and I'm willing to help make it stronger and more generalizable. To summarize, the main point of my research goal is to reduce the annotation cost. Each aim specifically focus on the component in the workflow, selecting the important samples for annotation, develop a strong model with annotation, and extract generic knowledge directly from the unlabeled images. Altogether, my goal is to develop the competitive AI system and also make this development procedure faster and with lower annotation cost. So we hypothesize that we can do similar or even do better, and we did it. So the first accomplishment is the active continued fine-tuning, which can select the most informative and representative samples from the entire data set. And the second accomplishment is called UNet++, which aggregates multi-scale image features to boost the performance even higher. And the third, we develop a model genesis, which can establish basic knowledge in medical images and makes the model perform much better, even with the small amount of annotated data. So this research direction is very promising, exciting, and significant, particularly for medical imaging domain. Because of the difficulty of annotating medical images, it's not easy to collect the millions of annotation for most medical specialties. Therefore, most medical tasks will fall into this blue area. And essentially in this area, the red learning curve, which we have achieved, will represent the annotation-efficient deep learning, and it can truly make a huge difference compared with the conventional deep learning approaches. To further validate the annotation efficiency of the proposed method, we participate in several imaging competitions. We are ranking number 3 in pulmonary embolism detection challenge, organized by a group from MIT. This PECAD was developed using our dataset and directly evaluate on the images provided by the challenge. without using any training data from the challenge. So this result shows our system is fairly robust to different images from different hospitals. And UNet++ and the models genesis was also used for liver tumor segmentation competition. And we are ranked #1 among all the teams. This work was done by Shivan and in his master degree thesis. And I also have written a book chapter that gives an overall overview of AI in medical image interpretation. In this chapter, I review several unique opportunities that AI can bring to medical imaging. And also I discuss some of the barriers when applying AI to medical imaging. The lack of annotation is of course one of the biggest challenges, and I have been focused on solve this challenge in this talk. And I think contribute to this chapter is a great opportunity for me to extend a broader view to the entire field of medical image analysis. And finally, I would like to thank all the help from my advisor, Dr. Liang, and also my dissertation committee member, Dr. Shortleaf, Dr. Greens, and Dr. Lee, as well as Dr. Godway, and Dr. Devarakonda. And thank you for your time. And please let me know if you have any question, comment, or suggestions.